Okay, good afternoon.
Good afternoon, sir.
Yeah,
Good
good
afternoon, sir.
afternoon. Yes, very good afternoon to all. So, in the previous class, we understood how to reduce the use of registers. So, when you have the lack of registers, so how to modify our own implementation such that the usage of the registers is reduced. Okay, that is what we looked in. And then if you still need more variables, okay, than the available registers, so then you can go for using the map and the field assembler directives to create the variables inside the memory. So again, when you're creating the variables inside the memory, you can go for creating of your required size. So if you want a memory for storing a 4-byte integer, you can allocate the memory for 4-byte integer, and also you're free to specify the address from where it has to start. And then if you want to declare an integer of 2 bytes, you can go for declaring an integer of 2 bytes. Okay, so this is what we looked in. And now the other thing that we are going to understand, the next optimization technique, is how to store multiple data values in one single register. Say if my data is of 32-bit, so then I can only store one data in my register. So if I say my data is not a 32-bit data, and if my data is a 16-bit data, in my register, which is of capacity 32-bit, so it is possible for holding two data values. In one single register, you can store two data values. So if I say my data is only 8-bit long, so then in one single register you can go for storing 8 different datas. Okay, so you can just imagine now how many registers you'll be saving, and also the performance. So if you say, for example, I have an 8-bit data and I'm using a register to store, in one single register I have stored 8 datas, okay, and each data of size 8 bits or a byte. Now, just by reading one register, it is possible for me to access all the 4 data. Okay, and so that is what the trick we are going to learn now. How to store, if in case if your data length is smaller than if it is only 8-bit or 16-bit, how do you store multiple datas in one 32-bit register? Okay, and doing this, okay, so the tricks we learn now, and applying these tricks, what it will reduce the code size, and it will also increase the performance. So that is what we see now. Next, say in order to explain you people how it can be done, how you can go for storing two data values in one single register. Now here I'm considering the example where I'm assuming my data values are 16-bit values. I'm assuming my data values are of 16-bit, and how to store these 16-bit data values in one single 32-bit register. Now, what I'm assuming, this 16-bit data values again, say one is index value, another one is the increment value. So I got to write something like this. This is the high-level statement what I've written. So what I'm doing, first I'm from the table, from this particular index, I'm reading some sample. And then next I'm going for incrementing this index by some increment value. Okay, so these are this index as well as increment are 16-bit values. So then for storing this index and increment, instead of wasting two separate registers, two 32-bit register, now we will find out a device or a trick where we can go for storing this index as well as increment in one single register. Now, how are we going to pack both the 16-bit values in one single register? So something like this. So I have the index stored at the most significant byte position. The higher or the upper 16 bits is my index, and the lower 16 bits is my increment. Now, say I'm storing something like this. Next, how do I go for accessing these things? Now I can access them. See, if I want to access this 16-bit data, index data, which is stored at the most significant 16 bits. Now I got to perform 16-bit right shift. So I got to perform 16-bit right shift and then take this to the LSB position. So that gives you the index. And similarly, if I'm interested in accessing the increment, so then I have to go for masking the index. Now for explaining this very clearly, let me take a simple example and show you. So I have a notepad open here. So let me write, so my index, say index value is 0, 0, 0, 5, and my increment value is 0, 0, sorry, is equal to 0, 0, 0, a. Okay, so this is what is my data. So this is one 16-bit number and this is another 16-bit number. Now what I go for storing it something like this as one single 32-bit register. Say I'm in the register R1, I'm storing this 0, 0, 0, 5, then 0, 0, 0, a. Okay, now I want to access, let me write the binary equivalent of this. What is the binary equivalent of this? Writing here 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and 5, 0, 1, 0, 1, and then 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, then 1, 0, 1, 0. This is my binary equivalent of this data. So this is one 16-bit data and this is another 16-bit data. Now if I want to access this, if I want to access only the index value, which is 5, what is that I got to do? I got to take this number, this entire 32-bit number, then I got to go for performing. So this 5, I need to take it to this position, this position. How do I take it to this position? I got to perform 16-bit right shift. So perform 16-bit right shift. So if you perform 16-bit right shift, what is that you'll get? So you get this. So 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and next this 16-bit, it comes to the LSB position 0, 0, sorry, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, then 0, 1, 0, 1. Hope you understood. Now what is the value of this? 0, 0, 0, 0, 1, 2, 3, 4, 5, 6, 7, and a 5. Hope you understood.
Yes, sir.
So you perform 16-bit right shift. So if you perform this 16-bit right shift, this entire 16-bit which is at the MSB position now comes to the LSB position, and the value of this is 0005. So this is also 5 and this is also 5. So, okay, this is what the trick we do. What we do, we take the content which is there in the register R1, okay, and we right shift it by 16 times. So this gives you, when you right shift it by 16 times, it gives you the index. So what I'm getting is the index. So now similarly, how do I access the LSB position? So this, only this A I need to access. I don't want this right now. And A is already in the LSB position. So I don't have to shift. A is already in the LSB position. Only thing I need to do is I need to go for masking the higher 16-bit. So we got to mask the higher 16-bit. Now how do I mask it? See, something like this. R1, I do bitwise ending with what? 0, 0, 0, 3, 4, 5, okay, 4, 0, 0, 0, okay, ending with R1, ending with this R1 is this. Yeah, now here I'll just show you. So this is what mask the MSB position. Now how to mask the MSB position? So I'm showing you. So 0 0 0 and F F F F. Okay. So with this you got to do. So if you do the bitwise ANDing between the current value which is there in the register R1. In register R1 I have entire this thing. Now this thing I'm going to AND with this. Okay. Now R1 is this and this I'm doing. Now when I do ANDing of this with this, what will happen? My 16-bit, higher 16-bit will become 0 and what I get is the 0 0 0 A. Let us go for doing this. Let me write the binary equivalent of the 0 0 0 0 FFF. So 0 0 0 0 1. So this is what I'm getting. Okay. Now, so I do bitwise ANDing of R1, content of R1 register with this. So this is what I've written. Let me write now the R1 register. R1 register is this. If you do the bitwise ANDing, what is the result you get? This is 0 0 0 0 because 0 and this is 0 itself. Next year 0 0. Here it is. So 191 is 1. 190 is 0. 191 is 1. 190 is 0. Now what is this? This is nothing but 0 0 0 0 1 2 3 4 5 6 7 8 0 A. So we got 0 A here, and by doing this operation we got 0 A, and by doing this operation we are getting the index value, and the 0 A is nothing but what is the increment. Okay, people are able to understand?
Yes, sir.
Okay, so whenever you want to access the data which is stored in the higher 16 bits position, so you got to perform the 16-bit write shift that you can access now the data 16-bit data which is stored at the higher 16-bit position. And similarly, if you want to access the data which is stored at 16-bit data which is stored at the lower 16-bit position, you got to mask the higher 16 bits. How do you mask the higher 16 bit? By ANDing the content of the register R1 with 0 0 0 0 F F F F, because I want this complete higher 16 bits of data to get masked, and I want the same value which is present inside the lower 16-bit value to be present after the operation. That is the reason we are writing it as FFF. So I guess you people understood this.
Yes, sir.
So this is what the simple trick that we make use in order to retrieve the multiple data values stored in one single register. So same thing is written over here also. So whenever I need to take the index, so which is stored in the higher 16-bit position, I do 16-bit write shift. And similarly, whenever I need to take this, access this increment, I go for masking the MSB. So most significant byte or the most significant 16 bits are masked. Okay. So with this, we'll go to the next slide, and then this is okay, not necessary now. So we have something called as single instruction over multiple data stream. So a person by Flynn has classified the computer architecture into 4 main classification. So this you'll understand in your 8th semester. So it's called as SISD, single instruction stream over single data stream. SIMD, single instruction stream over multiple data stream. And MISD, multiple instruction stream over single data stream. And MIMD, so multiple instruction stream over multiple data stream. Okay, that is also one more thing which you can do, but this is not required for us. Okay, so we'll study this in your 7th semester. Let me skip this. And next is summary of register allocation. So ARM has 14 available register for general purpose. So R0 to R12 and R14, 13 and 15. So they cannot be used for general purpose. So if it is inevitable for you to use R13, 14, and 15. So then you got to use them by taking the sufficient backup. And then if you need more than 14 local variables, then you can go for having the stack, use the stacks. And then it also suggests you to use the register names instead of the physical numbers, physical register number, because this way using the register names, so it makes easier for you to maintain and understand the code. Okay, and then go for storing multiple values in the same register. So if your data size is not 32-bit and if it is lesser than 32-bit, so when I say lesser than 32-bit, either it could be 8-bit data or 16-bit data. Now you can go for storing this 8-bit or 16-bit data, multiple datas in one single register. Okay. So these are the summary with respect to the register allocation. Next is conditional execution. So this is another important benefit what we have in the ARM7 design, because for majority of the instruction you can go for embedding the condition. Now because of this, so a lot of efficiency is improved and also the code size is reduced, because you don't have to write an additional conditional statement for executing a statement. So I want to make a statement condition dependent. So it is not necessary for me to write a separate conditional statement and write the statement whose execution is required only after that condition is satisfied. So instead of writing two or more statements, so now in just by writing the instruction, we can go for embedding the condition within itself. So a lot of code size is also reduced. So you have the instruction embedded with the condition. So only if that condition is true, then we have the instruction getting executed. Otherwise, the instruction is not executed. So this is another, so what, optimization. So embedding a condition within the instruction is another optimization technique where you can go for improving both efficiency as well as you can go for reducing the code. So reducing the code length also makes the performance of the program, okay, good. So we have the examples here. Now what this program, so there is a C code here and there is assembly code, equivalent assembly code here. Now what this C code is doing, let me write and show you. So if the value of I is less than 10, now what it does, it takes the value of I, say for example I value, I'm writing it as 1. So I1 is less than 10, true, it comes here. And then it is finding the ASCII value of the digit 1. Okay. Now I is 1 plus inside single quote I've written 0. Now what does it take? It's not going to take the value 0 or the integer 0. Instead it takes the ASCII value of 0. What is the ASCII value of 0? So anybody remember? What is the ASCII value of 0?
47.
No, 48. ASCII value of 0 is 48. Okay. Now, does it take 48? No, because all our computation assembly codes what we executed, okay, it takes in the form of hexadecimal number. Okay. Now you convert this ASCII value, which is a decimal ASCII value of 0 to hexadecimal. How much you get it as? 30H. 30H. Okay. Now to that 30, we're adding 1. How much it becomes? 31H, which is the hexadecimal equivalent of what? 49. So 31 is the hexadecimal equivalent of the decimal 49. Now what is this 49 now? 49 is the ASCII value of 1. And this 31 is the hexadecimal equivalent for the ASCII value of that 1, that is 49. Okay. Now I get it as 31, which is the hexadecimal equivalent for the ASCII value of 1. Similarly, if I give the I value as 2, what will happen? Again 2 is less than 10. 2 gets added with 48, it becomes 50. 50, when this is converted into hexadecimal equivalent, you get it as 32H. What is this 32H? Is the hexadecimal equivalent for the decimal value 50, which is nothing but the ASCII equivalent for the integer 2. OP people are able to understand?
Yes, sir.
Okay. Now, in case if I give the value of I so greater than 9. Okay, so 9 is also less than 10. Till 9 it is fine, it goes like this. So it goes for giving you the hexadecimal equivalent for the ASCII values of the integer value from 0 to 9. Similarly, if I input any number which is bigger than 9, say for example 10 I am inputting now, 10 less than 10 false it is, it comes to the else part. Now I value is 10. Now what I'm doing, from the ASCII value of uppercase A, what is the ASCII value of uppercase A? It is 65. All of you know this. ASCII value of uppercase A is 65. What is an hexadecimal equivalent of this? It is 41H. Now from 41H, how much you are subtracting? 10 you are subtracting. Okay, 10 minus 41 is 31H. 31H plus 10. How much it becomes? Again 41H, which is nothing but the hexadecimal equivalent for the ASCII value of uppercase A. Okay, so when I give 10, so I'm getting the hexadecimal equivalent of the uppercase A. And similarly, if I give 11, you'll get it as 42H, which is the hexadecimal equivalent for the uppercase B ASCII value. Uppercase B ASCII value is 66. You convert this into hexadecimal, it becomes 42H. Hope you people are able to understand.
Yes, sir.
Okay. Now, this is the high level code, and the same thing is written in the low level code. You can observe here. So compare I value with 10. So add on low. So if it is low, add 0. If it is higher, then go for adding how much? So this minus from the ASCII value of A, subtract 10 and add the current value to current value of the I to that. Okay, you get the ASCII value of the character A to Z, something like this. When if it is lower than 10, you get the corresponding digit hexadecimal equivalent for the ASCII. Okay, so this is the example. I have the working example also. We'll quickly do this. Okay, I'm copying this. Okay, let me replace this. Translating. So building, 0 errors and 0 warnings. Now debug. So look here. See, I'm moving 11 to the register R0, comparing 11 with 10. Okay. Now add on low. So 11 is not lower than 10. Condition is false. Okay. So 11 is nothing but B. B greater than A. No, false. Now what happens? This will not happen. So you'll not get anything in the register R1. It still stays 0 itself, and it comes to the next stat. So this execution of the statement is skipped now. It is skipped. Now here we are. Now what we are doing, from the ASCII value of uppercase A. Okay, let me write here. ASCII value of uppercase A is 65. So when you convert this into hexadecimal, it becomes 41H. Okay, so 41H minus 10, that is nothing but A. So if you do that, so you're getting it as 31H. Okay, now the result of this is 31H, and to that you're adding the value which is there in R0. In R0, how much you have? 11 you have. So 31 plus 11, you should get it as 42H, and this 42H is the hexadecimal equivalent for the ASCII value of uppercase B. Okay, and for 42, the decimal ASCII value is 66. So is that clear?
Yes, sir.
So when I give 11, it should give me the hexadecimal equivalent for the ASCII value of uppercase B. Now in register R1, you should see 42. Okay, I'm pressing F11 now. See, you got 42. Okay. Similarly, if I go for giving a value lesser than. So let me stop this. Now 1 I have given greater than 10. So now let me take lesser than 10. So let me take 1 itself. Okay. So you know ASCII value of 0 is 48. Now what I'm trying to print is the ASCII value of 1. ASCII value in the sense hexadecimal equivalent of that. Okay. I'm translating, building. Now go for debugging. Say 1 is the data which I'm putting in the register R0. Then I'm comparing 1 with 10. Okay. Now, yes, 1 is lower than 10. The condition is true. Now, what happens now to the ASCII value of 0, which is 48. Okay. So, 0 ASCII value is, remember this. So, you got to remember for 0, uppercase A and lowercase a. And the rest you can easily find. Okay. 0 is ASCII. 0 is as, sorry, 0 ASCII value is 48 and hexadecimal equivalent for this is 38. Now I have 30 plus 1, it becomes 31. In R1 you should see 31 now. So R1 has 31. Now what is that 31? So 1 ASCII value is 49. In hexadecimal it is 31 H. Any doubts? Hello?
No, sir.
Okay. So please do remember these three ASCII values. So there are a few things which you have to remember. See, for enter key, the key enter key which you press from the keyboard, ASCII value is 13. Okay. So let me write here. Enter key or return key. It's also called as return key. ASCII value is equal to 13D decimal. And the same thing in hexadecimal is 0DH. 0DH. And then for 0 I've already written. Okay. And for uppercase A it is 65. 65 and hexadecimal is 41H. And for lowercase a it is 97 and the hexadecimal equivalent of 97 is I get 61H. Is that correct? Is hexadecimal equivalent for the 97 is 61? Please check it.
Correct, sir.
Correct, no? Okay. This
Yes,
is all.
sir.
So please do remember for these things. So 0 you should know, uppercase A you should know, and lowercase a you should know. So these things because we more frequently use them. Okay, next. So I hope you understood with this. Now see how simple the program is now. So we haven't written separate conditional statements to check. So just look into the I level statement. So I level statement. So say this is all start and all you just ignore. But only three statements. Only three statements. So but look into the I level statement now. See I have written if, and if this condition is true, then I have written this. Else, so do this. Opening curly. So all these things. So you see how simple it looks now here. Compare, add low, add HS. Okay. So this is what the beauty of the conditional execution. It reduces the code size by lot and also improves the efficiency. And this was the example, and not one example, we have many examples also. So this is for counting the vowels. Now this is what the I level statement we write, something like this. If A is equal to C is equal to A, E, I, O, U. Okay. So vowel plus plus, and the same thing can be done in assembly code also. See. So test on equality A, and then test on equality not equal to this, it comes here. If it is not equal to this, it comes here, and then finally increments the vowel count. And then detect if a letter is, if C is a letter. How can you do that? See here. So if it is, if the ASCII value of C, the character which you are testing, if it is greater than or equal to uppercase A, and the ASCII value of the character which you are checking, if it is less than or equal to Z, then it is a letter. And similarly, if it is greater than or equal to uppercase A, less than or equal, sorry, lowercase a and less than or equal to lowercase z, again it is a letter, you go for incrementing. And how to do the same thing here? Okay, I have the working example for this as well. Okay, let me take this and see here. You can notice all these days, so we were directly using the register numbers, but for the first time we are running a program by using an alternative name or the variable name. So by using the rn assembler directive, I'm making C as an alternate name for the register R0. Okay, so let us go for doing this. See what I'm passing now, 66. So what is the 66? 66 is the ASCII value of the uppercase B. Is it a letter? Yes, B is a letter. Now the letter count should get incremented. Otherwise, no. So I'm copying this. I'll replace it. So, okay, stop debugging. Now, okay. Now I'm going to the debug. Okay. So now C is nothing but R0, temp is nothing but R1, letter is nothing but R2. Now see my C R0 got loaded with 66. 66 is nothing but 42 in XR. Now subtract. So what is the temp got? 1 it got. Compare 1 with Z minus A. So okay, subtract an I. Okay. So now compare an I. Now add ls. Now is just 66 a letter? Is this the ASCII value of the letter? Yes, it is a letter. Now temp is 1, which is what? Yeah, so lesser, which is lesser than the z minus a. Now what happens? So we have the letter count getting incremented. Letter is nothing but the register R2. If you just observe R2, it becomes 1. That becomes 1. That means, so this is the letter. Okay, 66 is the uppercase B. Next. Next is looping constructs. So we have already written the looping constructs. So we used to do the write the conditional branch statement. If the condition is satisfied, true, loop, loop 0. All these things we have done. Now what type of looping constructs are fastest in ARM? So the loops which you write, the countdown loops which you write, are much faster than the count up loops. Say you got to, what is a countdown loop? A loop which starts from a higher number, and every iteration the count is decremented, and we repeat this until the count becomes 0. So remember, compared to the count up loops, the countdown loops are much faster. Okay, so the loops which starts from the higher value and counts down towards 0 are the much fastest loops. Okay, so now, so whenever you're trying to write a looping construct, go for writing using the countdown approach, because that way it is much faster. Okay, so and then we understand to implement how this countdown loops can be implemented. So what are the different ways of writing the countdown loops efficiently in the assembly? And we also understand unroll loops for maximum performance. This we have already understood, because we have already done examples on unrolling the loop, and we have also seen how the performance of the system improves. So our focus will be main on how to implement the countdown loops, not the count up loops. We're not considering, because countdown loops are much faster than the count up loops. So first thing that we are understanding is countdown loop from n to 1 inclusive. So we are not going to 0. So we are stopping at 1. Okay. So countdown loops, how to implement a countdown loops? which starts from n and goes till 1 including 1. So here is the example. See, I have move I is equal to n. So I is some register which is initialized with some high value. Now what I'm doing on every iteration of the loop, so I write the body statements here. So loop body goes here, and after that, after all my statements inside the loop body gets executed, I go for subtracting 1 from the I, and then I check branch on greater than to loop. If I value is greater than 0, so go back to loop and repeat. Now how the iterations goes here, how the I is going to take the value. Initially I value is n, next n minus 1 it becomes, next n minus 2, n minus 3, n minus 4, like this till 1, okay, including 1. For even when I value is 1, the statements which are written inside the loop body gets executed, and it stops only when the I value becomes 0. Okay, next. So decrement the countdown loop which starts from n and goes till 0. Okay. Now any doubts in this? The countdown loop starting from n to 1,
No,
starting
sir.
from n and going till 1. Okay. Now from n to 0, inclusive 0. Now what we are doing here? So only difference, same thing as we understood here. Okay, see, I'm taking some higher value, from that I'm subtracting 1. Okay, I'm making it to I, and my loop starts here, my loop statement goes here, and this is how it starts. I is starting from n minus 1, then to n minus 2, and then till 0. Okay, now here instead of BGT I'm using branch and greater than or equal to loop. So branch and greater than or equal to loop. So now here, see, it is starting from n, but on when the statements, body statements are getting executed, so the value of the I is n minus 1. So n minus 1 to 0 is nothing but n values. Okay. Next. Again countdown loops where we got to count from n to n by 3, inclusive of n by 3. Okay, say here n value again I'm taking, say for example, so to understand it clearly, say n value is 30. So n value is 30, that is what I'm assigning it to I. Now initially the loop body statements execute, and next what I'm doing, I'm subtracting not 1, so I'm subtracting 3 from the I value, and then I check branch and greater than to loop. Now what happens now? So 30, right? So it goes 30 by 3. How many iterations it will cover? 30 by 3. That is nothing but how many iterations this will go? 10 iterations. Understood?
Yes, sir.
So if I want 15 iterations, what I have to do? So I got to go for subtracting 2, that is 30 by 2, that is equal to 15. It will go up to 15 iterations. Okay. So this is the countdown loops from n to n by 3, including that. Okay. N by 2 also you can do whatever you want. Next, other counted loops. So till now we understood countdown loops, but positive countdown loops they were. Next, now other countdown loops like negative indexing. Okay, so just look here. I have RSB. I'm doing n0. What this is do? 0 minus n it will do. Now what is the value of I now? It is minus n. Okay, I'm starting from the negative number, and then body loop goes here. In the first iteration the value of n is minus n. In the next iteration it become minus n plus step. So this step can be plus 1 or plus 2 or plus 3, something like this. So branch on lesser than to loop. So as long as it is lesser, see, it starts from minus n and it goes till 0. So this is the again negative indexing loop. I guess if people understood with this.
Yes, sir.
Okay. Next, logarithmic loops are also possible. Now, what are logarithmic values? So you can see here. Say I'm taking the value of I as 1. Okay. So I is 1. Say this is 1. This is 1. Okay. Then n value I'm taking as 4. Now what I'm doing, on I, I'm performing logical shift left by how many times? N value is 4 times. So if I perform shift left by 4 times, so what will happen? So this 1, initially it is here. When I shift 1 time, it becomes 1 0. So when I shift it for the second time left, it will become 1 1 1 0 0. So this is for the first time shifting. So this is for the second time shifting left. So when I shift it for the third time, I get it as 1 0 0 0. So the third time. Okay. Now when I shift it for the fourth time, so this is nothing but your 2, this is nothing but your 4, this is nothing but your 8. And when I shift it for the fourth time, because n is equal to 4, I get it as 1 0 0 0 0. This is nothing but your 16. Okay, initial value of I is 16. So initial value of I is 16. Next what I do, so the body statements are executed, and after that I is updated. How I is updated? I perform logical shift right by 1 bit. Now when I perform logical shift right by 1 bit, so this 1 4 zeros, what it will become? 0 1 0 0 0. This is nothing but 8. So in the next iteration, it becomes 0, 0, 1, 0, 0. That is nothing but 4. And in the next iteration, it becomes 0, 0, 0, 1, 0, which is nothing but 2. And in the next iteration, it becomes 0, 0, 0, 0, 1, which is nothing but 1. Now, how it is going to iterate? So it's going to iterate something like this. So first iteration, the value of I is 16. Next iteration, it becomes 8. Next iteration, it becomes 4. Next, it becomes 2. Next, it becomes 1. Okay. So if you take n is equal to 4 and you're going with the logarithmic indexing, something like this, so it goes for how many iterations? 4 iterations. Oh, sorry, 5 iterations. Hope you understood.
Yes, sir.
So n is equal to 3 if you take. Okay, so this is skipped. It starts from here. So how many iterations? 4 iterations it will do. So I guess if people understood what is logarithmic indexing is. So looping by using the logarithmic indexing. Is it clear?
Yes, sir.
Any doubts, please, others? No doubts? Okay. Next is, so and here, so this is this loop structure counts from 2 raised to n to 1. So this is n is here, it has come as a superscript, but that is wrong. So 2 raised to n. So n should be here. Okay, make correction. So what is the value of n right now? 4. So 2 raised to 4 is nothing but 16. So it starts from 16 and every this thing it goes decrementing. Okay, next it becomes 2 raised to 3. Next 2 raised to 2. Next iteration 2 raised to 1. And final iteration 2 raised to 0. Something like this. Next. So next is the following loop structure counts down from an n-bit mask to 1-bit mask. Okay, now this is again easy. So just try to understand here. Say I'm taking the value of I as 1. Okay, and then I'm doing the reverse subtract operation. So this is how I'm doing. Okay, so reverse subtract, and then first I'm doing logical shift left by 1 bit. So I said n value is 1. Sorry. Yeah, 1 I'm taking. Sorry, this is, so what I'm doing, I am logical left shifting by 4 times. So this should not be 1, this is I. Okay. Now I value is 1. So 1, how many times I go to left shift? 4 times. So if I left shift it 4 times, what will happen? 1 0 0 0 0. This is what you get. Okay, and from that you're subtracting 1. So this is nothing but 16. Hope people are able to understand.
Yes, sir.
So 1, if I go for left shifting it by how many times? How many times? 4 times, because n value is 4. This is 4. This is what 16 I get. So 16 minus 1 is how much? 15. That is nothing but 1, 1, 1, 1. So this is what is my initial value. Okay. Now I come here. The body statement gets executed. Next, what I'm doing, shift, logical shift right by 1 bit. So I value I'm taking, this is the current I value. I'm shift writing it by 1 bit. So when I shift right, what will happen? So this one will go out of the register. Now we have this 111 remaining, and 10 is added to the left. Okay. So this was 15. Now this 15 has become in the next iteration how much? 7. Okay, people are able to understand.
Yes, sir.
Okay. Next, in the next iteration, what happens? This one will also go out. Now what is remaining is 1 1, and 2 zeros are there to the left side, and this is nothing but what? 3. So next it goes with for the third iteration with the value of I as 3. And in the next iteration, what happens? Even this one will also go out, and we are remaining with 1 and 3 zeros to the left. This is nothing but 1. Okay. So the last iteration one. So this is another. So this looping is called as n bit mask to 1 bit mask loop. Okay. Okay, people are able to follow this.
Yes, sir.
Okay. So this is another type of looping. Okay. And then this is unrolling, loop unrolling technique. So I don't have to explain again. So the same example we understood earlier also. So this loop is particularly now unrolled for 3 times. So all loads are written first, and from here to here it is first unrolling, second unrolling, and third unrolling. And these are the statements which we are writing in order to store the data. So the computed data, we are storing it into the memory locations, and then we are looping back. Now in this particular case, it is unrolled for 3 times. Okay, next. Now a summary of looping construct. So ARM requires 2 instructions to implement a counted loop. Say subtract, that sets the flag, and the conditional branch. And then unrolling the loop is another technique where you can go for improving the performance of the loop, or in general improving the performance of the program. And one more thing is you should not go for over unrolling the loop. So I unrolled it for 3 times and it is giving me better performance. Can I unroll it for 4 times? No, not possible. Why? So you got to see the availability of registers. So because in every unrolling you got to go for using the different register. So the number of unrolling what you do, so it is limited by the availability of the registers. Okay, first you got to see how many registers are available, and with that available registers, so how many, what is the maximum number of times the loop unrolling can be done. Okay, and then in ARM, so you can also go for implementing the negative and the logarithmic loops efficiently. So that is what you understood here. So negative and the logarithm loops can also be implemented, and do always remember the countdown loops are much faster than compared to the count up loops. Okay, so here we are done with the module 2. It's fully complete. So from the next class onwards, we got to start the module 3. Okay. So any doubts still here? So if you have, we can discuss with me.